All right, let's take a look at problem 2 from chapter 10. So at 542 Kelvin and 21.7 bar, the system ethylene benzene is in vapor liquid equilibrium. Available data for the system are given in the table below. Fill out the missing information on the table. All right, so we have a binary system at vapor liquid equilibrium. All right, let's solve problem A, and then we'll move on to B. All right, so the key is if I have a system at vapor liquid equilibrium, okay, I need to remember what I actually, have to work with, right? And the key is going to be in chapter 10, now that we've talked about vapor liquid equilibrium and binary mixtures, is that we have the fugacity of component I in each phase is going to be equal to the fugacity of component I in the liquid. It's going to be equal to the fugacity of component I in the vapor. And if I expand out my fugacity, that's going to be the fugacity coefficient of component I in the liquid times its partial pressure, so mole fraction times P, is equal to the fugacity coefficient of component I in the vapor times its partial pressure, so Yi times P, where the pressure in the two phases are the same. So I have an equality of fugacity, and then I have that, and I'm going to put my mole fraction first. Xi times Phi-L is equal to Yi times Phi-V. Okay, so the key in terms of solving part A is just applying, right, and remembering my iso-fugacity equation. All right, so now if I look at what we have, so I've got the fugacity of component I in the vapor, okay, but I'm missing the fugacity in the liquid, the fugacity, in terms of notation, this is, xi, right, then I have rows for component 1 and component 2. So this would correspond to x1, this would be x2, y1, y2, and so on and so forth. All right, so here I've got the fugacity of component 1 in the vapor, I'm missing fugacity of component 1 in the liquid, and then I have fugacity of component 2 in the vapor, and I'm missing fugacity of component 2 in the vapor. So the first thing I'm going to do is I'm going to apply my iso-fugacity equation to fill that in, right? So namely, I know the fugacity of component 1 in the liquids equal to the fugacity of component 1 in the vapor, right? So this is just going to be 7.150, and this will be 9.686. Okay, if I can write it on here. 686. So just in applying my iso-fugacity equations, since I know the fugacity of each component in the vapor, then I know the fugacity of each component in the liquid. Okay, cool. Now let's see if we can move on. So what I'm going to tackle next is over here, right? I know the fugacity of component I in the liquid, and I know the fugacity of component I in the liquid. So here I expanded out my fugacity in terms of coexistence, but just in terms of expanding, right, I know the fugacity of component I, right, in the liquid, right, is going to be equal to fugacity coefficient of component I in the liquid times its partial pressure, right, and I can do the same thing for the vapor. Okay, so what I'm going to apply is if I know Phi-L and I know Fi-L, well, the question is, can I solve for Xi? Okay, well, let's see. So if I write this out for component 1, fugacity of component 1 in the liquid is going to be equal to x1 times phi1L times P. So therefore, solving for x1, x1 is going to be equal to F1L over phi1L times P. Okay, and I should add, right, we're given P is 21.7 bars, right, and that has the same units as F1L, which is also in bars. Okay, so cool. So since I know phi1L, I can solve for x1. Okay, let's do it. Okay, I'm going to make a new script, and I'm going to call this problem 2. Okay, and so in terms of what I need F1, I need P. So I'm going to have F1L is equal to 7.150. P is going to be equal to 21.7. And then phi1L is 0.531. phi1L is 0.531. Okay, so in terms of solving for x1, x1 is going to be equal to F1L divided by P times phi1. Okay, cool. So if I run it, I've got to save it. Okay, so if I run it, I get the x1 is 0.6205. So this is 0.6205. Okay, cool. Well, then I could get x2 because I know x2 is just going to be 1 minus x1. Okay, so x2, I know it's going to be 1 minus x1, right? My mole fractions need to sum to 1. So make this. So x2 is 0.3795. Okay, so now I've got x2, 0.37. Okay, and all I applied there, right, is remember that my mole fractions need to sum to 1. Okay, cool. All right, well, what else can I get? So now I've got x1, x2. Oh, so since I have fugacity of component I in the vapor here, right, I should be able to do the same trick since I know fugacity of component 2 in the vapor and fugacity of coefficient of component 2 in the vapor. I should be able to solve for y2, right? And then once I have y2, I should be able to get y1. Well, let's put it in practice. Okay, so it's going to be the same thing. So the fugacity of component 2 in the vapor is going to be equal to y2 times phi2v times p. So solving for y2 is going to be equal to f2v divided by phi2v times p. Okay, so let's put in practice. So f2v is going to be equal to 9.686. Now I need phi2v, and that's going to be 0.844. This is 0.844, 0.844. And then p is up there. So y2 is going to be equal to f2v divided by phi2v times p. And then y1 is going to be equal to 1 minus y2. Right? We'll get it all at the same time. So y2 is 0.5289. Okay, 0.5289. And I don't know if it's 0.5289. And then y1 is 0.4711. Right, so actually component 2 is the most volatile component, right, because y2 is greater than x2, whereas x1 is greater than y1. Okay, so I've got my x's, I've got my y's, I've got all my f's. Now let's get the rest in terms of phis. Okay, well, so now since if I start with phi1v, so now that I have y1, okay, I can just apply, right, my same fugacity expansion equation. Right, so it's going to be, since I know f1v, okay, that's going to be equal to y1 times phi1v times p. So therefore, phi1v is going to be equal to f1v divided by y1 times p. Okay, and so I'll solve for phi1v, and then the same thing in terms of phi2l. Okay, I can do that, and it's going to be, well, f2l is equal to x2 times phi2l times p. So phi2l is going to be equal to f2l divided by x2 times p. Okay, cool. So let's get a new block here. And I already have f1v, I have y1, I have p. So it should be phi1v is equal to f1v divided by y1 times p. and then we had phi2L was equal to F2L divided by X1 times P. So if I run it, V1 F1V, hold on. Oh, did I get this right? I need F1V. F1V was given up here, right? F1V is 7.150. So I never defined F1V equals 7.150. And actually, I'll do F1V is just equal to F1L. And then F2L is equal to F2V. Right? That way I don't have to type them again. So I get that phi1L is 0.6994. 0.6994. Okay, and then phi to liquids 0.7193. Okay, cool. And so now just to kind of comment at things, 0.7193. All right, so we said component 2 was the most volatile component, right? Because y2 is greater than x2, so it's the most volatile component, all right? And we see that, well, we compute that the fugacity coefficient of component 2, right, in the vapor, let's see, is this, hold on, I'm trying to rationalize myself because something doesn't quite seem right. So if I look at this equation, right, since x1, if x1's less than y1, well then phi1L, right, should be greater than, oh, okay, all right, well, hold on, let me, so this makes sense, right, because if, so if I were to write this for component 1, since x1 is greater than y1, well then phi1L should be less than phi1V, right, and that's exactly what I have, phi1L is less than phi1V, okay, got it. So if I look at component 2, so now y is greater than x. So if x is less than y, then phi1L should be greater than phi1V. But I don't get that. I get phi1L is 0.7193 when phi1V is 0.8444. Okay, so question is, did I write something down? And it's, so if 1 worked out, 27193 is what I computed there. So the question is, did I make an error somewhere? And so this F2L, oh, it's right here, right? Instead of X1, this should be X2. Okay. So now if I run it, okay, this is 1.1762. 1.1762. Now we're good. .1762. Alright, so component 2 is the most volatile component, right? So y2 is greater than x1. So then the fugacity coefficient of my liquid is greater than that of my vapor. Okay, cool, right? Got it. So that is part 1, or part A. And so, I did a quick sanity check and I realized I had a typo in my MATLAB code, right? So always a good idea to look at your answer and make sure if it makes sense. Now let's look at B. So B says calculate the entropy of a vapor mixture with Y1 equals 0.3 mole fracs at 600 Kelvin and 12 bar. The reference state for each pure component is the ideal gas state at 600 Kelvin and 12 bar. So reference states pure ideal gases at the same temperature and pressure. Okay. Additional information that we're given is we're given the residual entropy at the same temperature and pressure, and we're given ideal gas heat capacities of the pure components, which are taken to be constant. Okay. All right, so now in terms of B, okay, in my head the key is is that we're given the residual entropy of my mixture, right, at a given temperature, pressure, and composition. And I remember that residual is equal to actual relative to that of an ideal gas. Okay. Well, in this problem, we're asked to solve for, right, essentially the actual entropy of my system. So what I want is S at T, P, and Y1, and that's going to be equal to my residual entropy at Tp and Y1, right, which were given in the problem, plus my ideal gas value at Tp and Y1. Okay, so I've got my residual value, right, check. Okay, so what I need to compute then is just my ideal gas value, right? So the idea is I know the residual value, well, let's get that of my ideal gas. Okay, so let's just say check, I've got that. So ideal gas value, okay, so for my binary mixture, that's going to be equal to, okay, what I'm going to remember is in general, right, in general, S is equal to sum over I, Xi, Si, plus delta S of mixing, okay, or we had sum over I, well, delta S of mixing was sum over I, S bar I minus Si, okay, but S is going to be equal to sum over I, Xi, Si plus delta S of mixing. Or for the case of an ideal gas, right, we have our analytic equation for delta S of mixing. So for my ideal gas for binary system, this will be Y1 S1 ideal gas plus Y2. Oh, and let me write functional dependence because we're going to have to cancel some terms. This could be Y1 S1, and this is pure component, okay, at the same TMP, plus Y1 S2 ideal gas at the same TMP, plus, okay, delta S of mixing. All right, I'm just going to write delta S of mixing for now for the case of an ideal gas. Okay. In writing this, all right, first is we're taking our reference date to be ideal gases at that same temperature and pressure. So what that means is we're taking S1 ideal gas and S2 ideal gas at TMP to both be 0. Okay. Cool. So now we have S ideal gas at Tp and Y1 is equal to delta S of mixing of my ideal gas. Now remember, for an ideal gas, delta S of mixing is equal to, well, I remember sum over I, Yi log Yi. Okay. Log Yi is always going to be negative since Yi is less than 1. So this is a negative to make delta S of mixing positive. Then I multiply by R just to give myself the correct units, right? R and S have the same units. So for my binary mixture, this is going to be minus R times Y1 log Y1 plus Y2 log. Let me see if I fit it in here. Y1 log Y1 plus Y2 log Y2. Cool. So putting it all together then, my entropy at Tp and Y1 is going to be equal to my residual entropy at Tp and Y1, which are given in the problem statement, plus, I should say minus R Y1 log Y1 plus Y2 log Y2. Okay, let's do it. Okay, so that's problem 2. Let me make a new one for, and we'll call this problem 2a, since we're going to have new variables. Oh, 2b dot m. So we were told y1 was equal to 0.3. Okay, and then SR. And what's interesting is I don't even actually need any of the heat capacity values that were given. SR was negative 1.8, and this is joules per mole Kelvin. Okay, so it's in SI units, negative 1.8. Okay, I'll make a note that's joules per mole Kelvin. Okay, so R, that's 8.314. Also joules per mole Kelvin. That's the only one I remember. Okay, so then S, which is going to be in joules per mole Kelvin, is SR minus R times Y1. Oh, and let me make it easier. That's Y1. Y2 is going to be 1 minus Y1. So SR minus R times Y1 times log Y1 plus Y2 times log Y2, right? And MATLAB LOG is natural log. So cool. So I get then to S is 3.2787. Okay. And let's make sure. So Y was 0.3. Cool. We're at 600 Kelvin and 12 bars, but our reference state's ideal gas also 600 Kelvin and 12 bar. Right, cool. Yeah. So the entropy of my mixture then is going to be equal to boop boop this value here of 3.2787. 3.27, and that's just based on 3287 given the reference states provided. 3287 joules per mole Kelvin. Okay, cool. So there's S, and that's relative to adopting an ideal gas or a reference state of ideal gases of my pure component states at the same TMP. Okay, that's problem 2. I hope that helps. We'll see you in class.